So good morning. Today we're going to talk about quantum materials and size confinement and quantum effects in nanotechnology. But first I want to give a broad overview of the extent to which our own senses can divine the properties of materials in a few different modalities. We're eventually going to focus our attention on vision and thus light-matter interactions, which will set the stage for our discussion of quantum confinement and quantum dots, semiconductor nanocrystals, quantum dot LED displays, solar panels that use quantum dots, and other types of nano-enabled optoelectronics. But first, I want to talk a little bit about how we perceive the world based on nanoscale phenomena. So when we think of a surface that we touch, what we are doing is creating mechanical perturbations in our skin that are being transduced through the skin and through the subdermal structures that are interacting with little nerve endings. And for light touch, these nerve endings are mechanically sensitive. They usually have a type of ion channel, most commonly a piezo ion channel, which when you look down at a cell surface, so you've got this phospholipid bilayer in the cell surface. And then in the middle, you have this transmembrane protein, which is in itself is a very sophisticated nanotechnological machine. And this particular one is called an ion channel. And what the ion channel does is opens and closes with respect to any number of environmental stimuli. And what would those environmental stimuli be? Well, in the case of touch, we're taking very small forces and we're straining the cell membrane in some way. And this is the cell membrane of a neuron, for example. And the cell membrane of a neuron that is mechanically sensitive will perturb in some way, will open and allow the exchange of ions between the outside of the cell and the inside of the cell. And this exchange in ion currents will actually change the electrical potential of ions between the outside and the inside. And that sudden change in potential will initiate this cascade process called an action potential, which will go from the tip of the neuron all the way to the brain eventually. There are many complicated steps of multi-sensory integration, multi-neuron integration to give you the full range of experience, but let's just take the sensation of light touch. So in light touch, you are scanning your fingers across a surface and it sort of feels kind of tingly, right? There's a little bit of a tingle, and that tingle that you register at the fingertips is in part contributed to by a structure called the Meissner corpuscle. And the Meissner corpuscle is a blob of tissue that surrounds a nerve ending. And this is the backbone. And this is the brain. And the Meissner corpuscle has a cell body here, the Meissner fiber has a cell body here near the spinal cord, and it terminates in a few different branches here. And at the tip of this branch, we'll zoom in again, and at the tip of this branch, there is a structure here called the Meissner corpuscle. And together with the nerve ending, the Meissner corpuscle mediates these low threshold mechanical signals like gently touching the desk in front of you. And this Meissner corpuscle and the Meissner corpuscle, which surrounds the nerve ending, that structure together, is engineered in such a way, loosely, engineered in such a way to respond best to vibrations between around 10 to 200 hertz or so. And there are corpuscles deeper in the skin called the Pacinian corpuscle, which will respond all the way up to say 1,000 hertz. And so when you're, say, stroking your fingers here, but maybe you feel some faint vibration in the palm of your hand, or maybe even up the arm, those are a bunch of different nerve endings responding, but maybe Pacinian corpuscles are responsible for some of the higher frequency vibrations that you feel. But the key is this generation of an action potential, which is the flow of ion current that kind of looks like a cascade. You can read a book on neuroscience to learn more about how this works. And it terminates in the cell body right next to or really behind the spinal cord, called the dorsal root ganglion, a ganglion being a bunch of cell bodies. And then there may be some projections within the spinal column, and then there's another projection up to the brain. And this is the sensory aspect of tactile perception, just highlighted for the one very specific case of light touch that's mediated by the Meissner corpuscle. There are maybe 20-ish types of mechanically sensitive or chemically or heat sensitive or pain sensitive nerve endings in your fingertips. And each time you interact with an object, you're engaging some number of them in some proportion. And that sensory information is integrated first at the level of the spinal cord, and then in a deeper brain region, and then in a more surface level brain region, which is where you put the sensory information and the emotional response that you get from deep brain regions into context, or the cognitive response. And can a pain signal, for example, signify something good or something bad? And picture going to the gym or being forced to run a mile in gym class in high school and it being really painful. But then imagine that maybe in some other context, you are doing something painful, but you're doing it for a good reason. Like, say you want to be doing it. Say you are at the gym exercising because you want to be there. Or you're getting a tattoo, which is painful because you want how it looks like. Like you enjoy the art, and maybe you are interested in new ranges of experience caused by extreme pain. Not that I would know anything about that. And so the idea is it could be really painful, but then because it's in context, it's less painful. Like you welcome it. It's not something that is going to cause you to suffer, right? And so that's the cognitive, contextual level of processing that happens in the cortex, right? And it puts meaning to a signal. And so basically all of the senses interact with nanoscale and molecular phenomena. They're mediated by nanoscale and molecular phenomena in a way that leads to your ultimate perception. And I would say that the human nervous system is by far the most sophisticated piece of material science characterization equipment that has ever been conceived of. Think about it. A UV visible spectrophotometer can tell you something about the absorption, but it can't tell you about the mechanical properties of the material. It can't tell you about the surface energy of the material. It can't tell you anything about the acoustic properties of the material. The only thing it gives you is a blanket overlaid plot of how absorption scales with wavelength. That's all it gives you. There's some really sophisticated things like nuclear magnetic resonance. If you're measuring the properties of a molecule, what it's going to give you is how strongly certain nuclei interact with a RF frequency when held in place by a magnetic field. I can't do that. We can't do that, but we can do a lot more, right? And so when you think about descriptors of materials, you are pretty much, and chemicals and chemical products, you're pretty much always dealing with some nanoscale interaction. So if we think of, let's say, vision, or visual sense, the auditory sense, the olfactory sense, the gustatory, I'm going to use the scientific terms, the gustatory sense, and the tactile sense. Tactile sense being a bit loaded because mechanosensation in the body occurs in more places than just the skin. You feel things inside your body, for example, when you're in pain. You feel things inside your brain when you have a headache. You feel things inside your eyes when you have a headache. Your body often has mechanosensory perception that you may or may not be aware of. For example, internal regulation of blood pressure is mediated by fluid flow and hydrostatics and hydrodynamics within the vasculature, which you're not necessarily consciously aware of, except for maybe downstream effects. In the senses of the olfactory and gustatory senses, I'm just being kind of clever here, but this is, olfaction is your nose and gustatory is your tongue. The senses of smell and taste, these are molecular. There are certain protein ligand binding interactions that cause action potentials at nerve endings that activate and are sent to the appropriate regions of the brain. We're not going to talk too much about those, but they're similar to what I told you about the tactile sense, in that you have say you have some molecular receptor that has some amino acid residues. Let's just say that there's a serine and a lysine and an aspartic acid or something, and then you have some molecule that might want to bond here. Maybe there's an ionized oxygen group or something, and maybe there's something here where you can hydrogen bond. And how are we going to calculate all of these interactions? Well, we're going to get out our chapter 2 and do all of our calculations on the van der Waals forces and fixed dipoles and so on. And then we'll get a binding constant, which might be some number of kT, and then we might be able to predict if an action potential is going to be generated based on the binding of some molecule. And each olfactory and gustatory percept, that is tart or floral or bitter of hops and alcohol or something, is going to engage a symphony of these types of receptors that will combine to produce some percept after you've cognitively processed what it is. So these are mostly molecular. You can't smell a nanoparticle. It's too big. You can't taste the nanoscale components of stuff. They're too big. Tactile perception, you can kind of feel molecular detail. For example, in my lab 7 years ago, we did a study on if you can feel did I talk about this in the class already? That you can feel the differences between smooth and rough, between hydrophilic and hydrophobic molecular monolayers. Did I mention that in class? Yeah. So kind of tactile, but still it's an ensemble effect. Still it's a continuum effect. So continuum properties of molecules, but also nanostructured surfaces. That's what continuum, molecular, and nano and nanoscale. The auditory sense is pretty much always a continuum effect. What do we mean? We mean collective oscillations. Collective oscillations of, say, a piano soundboard or the bell of a trumpet. Collective oscillation, or the cone of a loudspeaker. Collective oscillations of materials that may be influenced by its nanoscale structure, and certainly is in most cases going to be influenced by its nanoscale structure, but it can be treated entirely as a continuum phenomenon. Once you know what the elastic response of a material is going to be, its thermal response, the level of its displacement, the way that it interacts under a moving column of air, the way that it resonates, that will tell you pretty much what you need to know in principle about the sound an instrument makes, or the sound that a loudspeaker makes, or the sound that knocking on this table makes. There is also a tactile component of audition. of the auditory sense. Because when you go, one of the reasons you pay the big bucks to go to a live concert is for the visuals, but also because you can feel the sound, right? You can feel the sound of a marching band going by. You can feel when a fire engine blows its horn. You can kind of feel that. And because there is a good deal of overlap between the frequencies that can be sensed by the auditory sense and those that can be sensed by the tactile sense. So the middle A on a piano is 440 hertz, which can be perceived by both the Meissner corpuscle and the Pacinian corpuscle in the hand. Vision, I want to spend the rest of today talking about. And University of Rochester is perhaps the best place in the world for visual science. So I'm going to paint with a very broad brush on how vision works, because compared to the median person at U of R, I don't know anything about vision. But I do know a little bit about physical chemistry and nanostructures, so I'll get to that pretty quickly. All right, so what are some visual properties that are mediated by nanoscale phenomena? Why do I say nanoscale and not atomic or molecular? Well, the reason I don't say atomic or molecular is because there aren't too many instances, though there are some, where the properties of a single atom can produce a visual effect. For example, inductively coupled atomic emission spectroscopy you can see a visible light from the ionization of certain types of metals as a means of figuring out how much metal you have in, for example, a sample of wastewater at a treatment facility. That's an example of where the visual sense and atomic and ionic physics actually can reach the eye. But can you see an oxygen molecule in the air? No. Can you see an ozone molecule in the air? Yeah, kinda. It's blue. Maybe you can't see one, but you could see a bunch of them. It's just because we're not sensitive enough. Incidentally, I may just be exposing my ignorance, but what color is water, really? You know, it really is blue. I didn't realize that until much too late in life. But in fact, when you micropebble the surface of a pool in San Diego that you wish you still had but don't anymore, and you make it in a nice tan color that looks like the bottom of a Caribbean beach, that color is not blue, right? But when you fill up the pool, it's like blue-green, and it kind of interacts the same way because it absorbs at a certain depth. There's enough light matter interaction to make it appear blue. Anyway, okay. What are some visual percepts? What are some visual descriptors? Actually, I'll do better. Who's ever bought paint at Lowe's or Home Depot or a store like that? And you have to select the finish. So you've got, let me see if I can do this from memory as a homeowner. So you've got matte here, then you've got eggshell, then you have satin, I may have these in slightly the wrong order. Semi-gloss, and then you have high gloss. These are rougher. On the nanoscale, they're rougher, they're more porous. Semi-gloss and high gloss, they're harder, flatter, less porous. Do you want to paint a bathroom in a matte finish? No, you don't want to paint a bathroom in a matte finish or an eggshell finish. The reason is because they're porous and the steam from the shower will get into the pores over time and generate mold. Semi-gloss and high gloss surfaces are designed so that when they solidify, the little latex particles that, by the way, are held in suspension by a combination of electric double layer forces and a tension between the van der Waals forces between them. But once you cast them on a surface, when they solidify, the particles are small enough that they have enough entanglements and all the proprietary stuff that I'm not going to be an expert in. But when the film of paint solidifies, it forms a very flat surface with very few pores in it. And so water is not going to be able to get in here and create mold in the shower, or because of the shower. What does this mean from the standpoint of optical properties and optical dispersion? So on the matte side of things, we have a rough surface, and this roughness can occur on the micro scale or the nanometer scale, probably some hierarchy of micro and nano scale. And so what happens when a collimated, that means a straight beam of light comes in, is that you get all kinds of different reflections. And some of them reach the eye from this axis, some reach the eye from this axis. And here's the eyeball. That's what I'm going to show as the eye. And what does it look like? Does it look directional anymore? Does it, can you see reflections that were created over here? Could you project? Would you want to take a movie screen and paint it with a matte finish, or would you want something that was more that was flatter? You would want something that was flatter, right? Because you need to be able to see a crisp image. You don't want it to be too reflective, because then you'll see glare on the screen. So there's a sweet spot. If you take a flat surface and you have a collimated beam, or say this is an image, when these light rays bounce off toward the eye, you will see a reflection. This is called specular reflection. This is called diffuse reflection. Diffuse reflection we typically think of diffuse reflection as coming from optical surfaces that have random roughness in them. If they have regular roughness in them, or they have a deterministic pattern, then you get interesting dispersive effects like prismatic effects, like hologram effects, things where you can manipulate light by a predictable way in which light is internally reflected in the microstructured surface before it exits again. So say, for example, I didn't focus group test this demonstration, so if it doesn't work, forgive me. But an iPhone has a deterministically structured surface, and if you bounce a laser, there are dots. There's a central dot where the reflection is, and then there are maybe 100 or so dots in a regular pattern around it. Can you kind of see that, or at least sort of see what I see, those little dots around the central dot? Okay. That's because the pixels in the phone screen are micron sized, and they have a bunch of internal reflection events that cause a degree of constructive and destructive interference that can be projected or that will appear in a deterministic way on the wall. If I had a ruler and I did some Bragg's law calculations of that pattern, I could tell you what the resolution of the screen is. But if I bounce the laser off this table, which is rough, relatively rough, so that when you draw with a pencil or a pen, it actually creates a line. If it's too smooth, then it won't create as nice a line. It's engineered to be that way, but it's rough enough so that if I shine the laser, I won't get that dispersive quality, because the roughness here is, the patterning here is random as opposed to deterministic. And that's the difference between diffuse reflection and specular reflection. This is like direct reflection, mirror-like. What is happening when light is reflected off a surface? Well, surfaces are made of protons and electrons, and there is an inherent charge separation when there's an inherent charge separation that you can perturb, that you can make more significant upon applying an electromagnetic wave. So an electromagnetic wave is an oscillation of an electric field and a magnetic field that's perpendicular to it. What on earth does that mean? Take a modern physics class. But the point is, when this oscillating electromagnetic wave strikes something that has a positive charge and a negative charge around it, you can get that electron cloud to oscillate the same way that you do in a London dispersion interaction, except that you're creating it from a light source, like the fluorescent lights in this room. Incidentally, why is the surface of the fluorescent lights textured? Why is there that diffuser panel in there? So that when you're writing on your page, your hand isn't casting an annoying shadow on the page. Casts a little bit of a shadow, but because you have these little hemispheres, sometimes they're hemispheres, sometimes they're pyramids, sometimes they're lines. Because you have those, you have light coming from every direction, and you have this diffuse type of light. You wouldn't want a bunch of spotlights in the room, because then when you wrote, you'd have 8 different, very distinct shadows of your hands on the paper. Okay. So when the light comes in, it oscillates the electron cloud about the nucleus of the atoms that make up the material. And when that oscillation stops, that energy is conserved and a photon is re-emitted at the same frequency. That's called scattering. It's specifically called Rayleigh scattering because of a professor named Scattering. No, just kidding. Professor named Rayleigh, and that's in contrast to something called Raman scattering, where the frequency of the photon that's re-emitted after this transient absorption event is either higher or lower than the frequency of the incoming photon. We'll talk about those in more detail in a little bit. Okay, so we have Gandalf here waving a magic wand of charge. And the electric field is going up and down and up and down. And then we have an atom, or the electrons around a molecule, that can be transiently polarized. And then when they settle back down, they re-emit a photon. And then the directionality from which this re-emission happens depends on the bulk structure of the surface. If it's flat, you get specular reflection. If it's bumpy, if it's nanostructured or microstructured, you get diffuse reflection. Okay, now that explains why things would reflect light, but what about why they absorb light or why they appear a certain color? So if you take white light is some combination of a bunch of different types of wavelengths. A bunch of different wavelengths can make white light. Why is it white light? We don't actually perceive white photons. We perceive photons that are more or less red, green, and blue. Red, green, and blue together make white to our perception. So we have nerve endings in the retina that have dye molecules like food coloring in them that are sensitive predominantly to red, green, and blue photons. And combinations of red, green, and blue together produce different levels of activation of those nerve endings. These are in cone cells for color. There's another type of cell, rod cells, for light and dark, for the amount of light coming in. And those cone cells together with combinations of red, green, and blue and the brightness can produce the entire visual gamut. Okay, so white light, a bunch of frequencies, a bunch of wavelengths coming in from these, say, fluorescent bulbs, and then some of those frequencies get absorbed. And the rest of them are reflected. In a surface that is entirely white, you have particles in there that don't absorb anything, or really don't absorb much at all. Anything that's colored white is pretty much going to reflect every wavelength more or less equally. But say you have something blue, like the back of this eraser. What color does it absorb? every other color except blue, or enough of the other colors that what's left excites enough cone cell absorbers for us to perceive it as blue. It's not literally that it absorbs yellow, orange, red, green in equal measure. It takes a bite out of some of that spectrum. And then what we're left with is predominantly blue, but not exclusively blue. Is a photon of a single wavelength being reflected back at you? Definitely not. Definitely not. What if I took a blue LED? What if I took a blue LED and shined it into the room? Would that be a narrower range of wavelengths? Yeah, it would be. If it was a laser, a blue laser, don't look directly at it, but say I had a blue laser, would that be a single wavelength? Very close to a single wavelength. There would always be some spectral broadening in pretty much any of these experiments just because of the band structure of an optoelectronic material. You'll always get transitions that overshoot the conduction band and the valence band, and that's going to give you some broadening of the emission. Now, what's the difference between this color and the laser or LED color is that color can be the product of reflection and absorption on one hand, or emission on the other, where the material itself produces the color as opposed to some other material making the color. Then you've got a bunch of complicated, reflections, scattering, and absorption events, and then they're reflected back to our eye. This actually in part explains why the primary colors in an art class are different from the primary colors in optoelectronic devices. Because in art, has anyone seen Bob Ross? Who could name like all 10 colors on his palette? Anyway, the basic number of colors that you need for artwork, that's all based on reflection and absorption. Whereas in optoelectronics, like looking at a computer screen, actually most computer screens, it's actually still absorption. But there are some that are increasingly based on emission. And with emission, you get more control over what wavelengths you can generate, what percepts you can generate in the brain, in principle, because you have control over exactly how much stuff you're sending, what proportion of wavelengths you're sending out into the world. Okay. The reflection piece is all related to this, the transient polarization and depolarization of electron clouds in matter. The type of percept that you get, high matte or high sheen, depends on the nanoscale arrangement of the surface asperities in the material. But absorption and emission occur when the frequency of incoming light matches the band gap within materials. What do I mean, the band gap? I shouldn't say matches the band gap, they match a gap between the electrons in the valence band of a material and the electrons in the conduction band of a material. That is to say, similar to the energy of the electrons at the oxidation potential of a material and the electrons at the reduction potential of a material. Let me say it in a third way. The electrons in the bonding orbitals of a material or the electrons in the non-bonded orbitals of a material. So sigma, sigma star, pi, pi star. Those three ways of describing the situation aren't exactly equivalent, but they're close enough for jazz. So absorption, emission, this is the valence band, and this is the conduction band. And we could be talking about a semiconductor, we could be talking about a nanoparticle, we could be talking about a semiconductor nanoparticle, a metal nanoparticle. The metal nanoparticles work a bit differently from this. They have something called a plasmon resonance, which is not quite what I'm talking about here. We'll talk about that later, but it's another way that color occurs in matter. Another way that color occurs in matter is through white light interference and resonance effects. But we're not going to talk about that right now either. Talk mostly about electronic absorption. And that covers, I would say, most things that have color in your environment are because of this type of process. And so light comes in. Light we'll abbreviate as h nu, Planck's constant, times the frequency. And this gap here is the band gap. In real matter, there are states, there are places where electrons can live above and below the band gap, but not in between in general, unless we oxidize or reduce the band gap or dope it with some other atom or other things that solid state material scientists can do, physicists can do to manipulate this. There is another concept where above and below you have some, say this is a high probability and then maybe a low probability and then a very high probability and then the band gap. And this is called the density of states. And similarly, you have a density of states up here. And the density of states determines the probability of absorbing a photon with a certain energy. So the energy is h nu, or the energy is hc over lambda, where c is the speed of light. Lambda is the wavelength. And the visible wavelengths are approximately 400 to 700 nanometers. 400 being violet light and 700 being red light. Is there anything intrinsic about them that makes them red or violet? No, it's just our brain. That's just your brain. It's just our brain making that association between that sensory information and that cognitive processing. Is there such thing as a cone cell receptor for yellow light? Not really. When you look at your computer screen, it has red, green, and blue color filters, but no yellow. So to get yellow, optical engineers have figured out how to give your retina a combination of red, green, and blue light that looks yellow. If you were to take an LED that was more or less monochromatic, and you had a band gap that was in the yellow range, so maybe, I'm gonna get the nanometers wrong, 600-ish? That would be a yellow photon, but it would be exciting the same proportion, relatively the same proportion of red, green, and blue sensors in your eyeballs as the red, green, and blue light coming from a computer screen. Two completely different spectral distributions. One is more or less monochromatic, one is highly polychromatic, but they generate the same action potential in your retina. Anyway, so this density of states above and below the band gap determine what color the thing looks like. And what happens to this light? What happens to this energy? Say you have an electron down here and it goes up here. Because of this absorption, say this energy matched this difference in energy between down here and up here. In most materials, that energy is going to be dissipated somehow. What do I mean by dissipated? It's going to, those atoms or molecules are going to bump into other atoms and molecules, and it's going to transfer its energy into vibration or heat, which you can sense as with a thermal camera, like an IR camera. And you can see where that energy originating from optical sources went, some of it. Some of it, you could even get it to dissipate by sound via the photoacoustic effect. There are any number of ways that this energy can be dissipated. Some types of materials are really good at re-emitting this light. So what happens is that you do get energy loss, but it doesn't dissipate into the material. It dissipates down to the band edge, edge, which happen right here and here. This is the highest point of the valence band and the lowest point of the conduction band. And when it dissipates down to the band edge through a process called thermalization, the electron can then go back down to the valence band edge and emit a photon. The emission of a photon can happen in a couple of different ways. The most common type of emission is fluorescence. In fluorescence, this is a quick process, happens almost instantaneously. The light comes in, the light is entirely converted into this jump from somewhere in the valence band to somewhere in the conduction band, followed by extremely rapid thermalization. So some of that energy is lost as heat. And then you have, it goes down very quickly, this elevator, to the edge of the valence band and emits a fluorescent photon. Does it have to land exactly at the valence band edge? No. It can land anywhere in the density of states, but it's more likely to occur where there's a lot of density of states. And that's the fluorescent photon. Because you've lost energy here, the fluorescent photon is the maximum wavelength of emission. The most probable emitted wavelength is of lower energy or higher wavelength than the incoming photon, because some of this energy is lost in the thermalization process. This is the normal case. The less common case for most materials is something called phosphorescence. And this is a more rare thing. Phosphorescence occurs because when an electron from the valence band goes up to the conduction band, there is a change in magnetic quantum number, or spin, where the electron goes from this state to this state with the transition. And a physicist would be able to tell you more about why this happens, but suffice it to say that the electron can't simply drop back down without changing its spin. And in order to change its spin, it takes a long time. It takes on the order of minutes or hours to get that phosphorescent photon back out. So does anyone have a glow-in-the-dark things in their childhood bedroom? That's phosphorescence. You charge up those stars or constellations or puffy paint or whatever, and then over time it decays back down. Okay, together, these two types of emission are called photoemission. Or photoluminescence. I have no idea if I spelled that correctly. However, you can get light to emit from a material with a band gap in other ways. You could have emission, where you are forcing electrons into the conduction band and then they decay down to the valence band. That's more or less how a light emitting diode works. You can modify the band gap with electrochromic effects, where you're changing the band gap by applying an electric field, or you're oxidizing or reducing this material with electrodes. So for example, if anyone's been on a 787 Dreamliner plane, there are no window shades. They darken automatically. They darken due to an electrochromic effect where the band gap is or the material undergoes some change in band gap by, say, a redox process, and then it basically turns dark, turns opaque. All right, that is a lot of material. Questions?